So in week one, we had seen introduction and overview of the semiconductor device fabrication. That is the history of IC, what was Moore's law, what was the precursor to these, like so the predecessors to these present semiconductors like diodes and triodes. Then we saw a basic process of the IC fabrication, what is the submerged arc electrode process, Siemens process, Czochralski float zone and wafer slicing. That is from the sand or silica that we have, how do we reach the silica wafer? And once the wafer we have got, how do we pattern it and so on. So this last particular portion, wafer fabrication overview, I think if you have gone through the week 2 lectures, each of these processes is explained in detail. In week 1, you have just an overview of layering, doping, patterning, heat treatments, and their examples in a few paragraphs. But in week 2 contents, I think there is an in-depth explanation of these. Each of these topics is given. So I hope that all of you have gone through the week 1 lectures. So has all of you gone through the week 1 lectures? So, and one more thing is that instead of keeping all the lectures to see it towards the end or just before the assignment submission, so each week find some time so that you are updated with the syllabus. So then only it will be useful to you. Otherwise, just for the sake of examination, if you learn, it won't be much of a help, I feel. So try to learn it as soon as it is uploaded, like a few hours each day in your leisure time and so and so. And for people who have not gone through the week one lecture, so this is the integrated IC circuit history. So this is a brief recap, and this is also updated on your website. You can download it from the drive link given in the announcements in the content section. So what was the diode, triode, the number of ports for each, and how did we reach the solid state transistor after that, and what is the Moore's law, we have seen in week one. Then the wafer size and their interconnects, and how the size of the wafers have been going on decreasingly in each year. And finally, an overview of the fabrication process. How do we do the material preparation of sands to silicon? So we'll have a few questions based on these things, and then we have crystal growth and wafer preparation. Finally, wafer fabrication and sorting, packaging. So each of these will be explained in detail in the coming weeks. So now it's just a brief overview. And finally, the silicon wafer manufacturing. In week one, this is the most important part, I would say. Like, how would we convert the sand or the silica into the metal electronic grade silicon? So the processes that are involved, the Siemens process, then how do we like make use of the Czochralski and the float zone processes? What is wafer slicing and grinding and so on? And finally, fabrications like layering, doping, patterning, and heat treatment. Just I'm just going through. Like for those who have seen the lectures, they might be able to recollect that these are the things that you have seen in week one. So based on that, I have prepared a few questions, and you are expected to take a few moments and answer each of these questions. So the first question is, the first electronic amplifier, a precursor to the modern day transistor is dash. A radio, B diode, C integrated circuit, and D triode. So anybody of you can unmute and answer.
Triode.
Yeah, and why is that? Like, what do you mean by a triode? Can you just give a brief explanation? What is a triode?
It consists of three electrodes. One is cathode and other is anode, and we have a grid between which whose potential is different. Potential can be modified.
Okay. So anybody wants to add anything more to the answer? The answer is correct. So anything anybody wants to add. So this is like a discussion. So anybody feels that if they have an additional point regarding the triode, they can contribute right now. I think somebody joined. Just so basically, as you mentioned, the triode has three electrodes, a cathode, an anode, and a grid, and the current between the anode and cathode is modified by applying potential across the grid. So that is the precursor to the modern day transistor. So similar to the modern day transistor, just three terminals, anode, cathode, and grid. And so in the transistor, we have a source, drain, and gate, and preceding to that, we had the triode, which had the anode, cathode, and the grid. So why is it a precursor to the transistor? Because it is very similar in the number of ports and their function, right? So it has a source, drain, and a gate. So next is, The Siemens process converts dash to dash silica to MgS, where MgS stands for metallurgical grade silicon, MgS to EgS, where EgS stands for electronic grade silicon, then EgS to single crystalline salt, or MgS to single crystalline salt. So, what does Siemens process do? Anybody?
MGS to EGS.
So, can you tell me something about what you know about the Siemens process? Like what kind of a process is it? Whether it's a chemical reaction or
Yeah, so it was done in a reactor at some high temperature.
okay,
You pass HCl gas onto the MGS,
okay,
and it forms an intermediate state, which is again broken down by the hydrogen, and the output is again the silicon.
silicon. Okay. So basically, the Siemens process is a fractional distillation process, and it is used for the purification of MgS. So which means that it will convert MgS into EgS, that is metallurgical grade silicon, into electronic grade silicon. That is, the number of impurities will be reduced. So it is converted from parts per million to parts per billion, the impurities. So basically what happens is that silicon is reacted with HCl in gaseous form to get trichlorosilane. So this in turn is then separated by a fractional distillation process and then reduced using hydrogen. So this trichlorosilane plus hydrogen will give us the electronic grade silicon plus HCl in gaseous form. So this is a looped process, and after few cycles of fractional distillation, the number of impurities will be reduced from parts per million to parts per billion. That is how we convert MgS, that is metallurgical grade silicon, to electronic grade silicon or EGS using the Siemens process. So is that clear for all of you? What is the Siemens process? So this is a live interaction session. So I seem to, and me and a few others only, seems to be the people interacting. So if you're not getting, please do unmute. I am happy to explain it again and again. That's why I'm here for. So have you got what the Siemens process is? So this is an additional point, like normal silica or sand is converted to metallurgical grade polycrystalline silicon using the submerged arc electrode process. And then MgS is converted to EgS using the Siemens process. Finally, EgS then has to be converted into the single crystalline gold, which is then sliced into the silicon wafers. That is done using the Czochralski and the float zone process. So, next question is, which of the following is an example of a heat treatment process? Iron implantation of dopants, silicide formation after metal deposition, spin coating of the photoresist, and electroplating of the metal interconnects. Which of the following is a process which involves heat? So, if anybody can unmute and speak. Like, am I audible to you all?
Yes, yes.
Yeah. So, which of the following is a heat treatment process? Like from the name itself, you might be able to understand something that is done at high temperature or which involves heat.
Is it electroplating of metal interconnects?
No, because electroplating, you see, is an electrochemical process. It's not always at high temperature, right? We are just like using two electrodes and using an electric potential. We are plating it in another oxide material, and so that doesn't involve heat. So again, spin coating of photoresist means it's just a coating process. So once coating is done, during the curing stage, heating is there. But actual spin coating of photoresist also doesn't involve heat. So option C and D are wrong. So which would you select between A and B?
Is it silicide formation?
Yeah, because before in the Siemens process, you have already told that silicon will be reacted with HCl at a high temperature, right? To get our trichlorosilane. Again, ion implantation of dopants, you see, ions are just like once the ions are formed out of the requisite material, it will be bombarded onto our substrate or whatever semiconductor we have. That again is an implantation process. It does not involve like heat. It just involves a potential difference where the ions are driven towards our semiconductor. So option A, C, and D are wrong. So that leaves us with silicide formation after metal deposition. So I think it's clear to all of you. Next is a wafer has two flats at 90 degrees to each other. The type of wafer is P111, N111, P100 or N100. They have two flats. So in these silicon wafers, once you're using for research and so on, so there is no mark, there nothing can be written on top whether it is a P111 or N111 and so on. So it just has a part of it cut in a particular angle so that we can identify what is the crystallographic plane and whether it's a p-type wafer or an n-type wafer. So for that identification, we'll create flats where a portion is cut off. So if a wafer has two flats at 90 degrees to each other, the type of wafer is dash. Like if anybody,
C.
yeah, uh,
C.
C, yeah, that's correct. So if you have made notes, you can refer to the notes also before answering. So C is the correct answer. So if you see here, see, for a p-type 111, what happens? It has no secondary flats. Like one port will be cut and that is called a primary flat. It has no secondary flats. So that is P111. So if it is an N-type 111, it has one primary flat and the second cut is there, or the secondary flat, it is 45 degrees to the primary one. So if both flats are at 90 degrees, that is primary and secondary are at 90 degrees to each other, it is P100. Again, if we have an N-type wafer, it will be at 180 degree to each other. This will be the primary flat and you can say this either a secondary or primary. So both of these flats will be at 180 degrees to each other. So this is the way in which you identify your silicon wafers in the lab. So is it clear for all of you?
Yes.
Yeah. So next is the first step in IC manufacturing is dash wafer fabrication and sorting, single crystal growth, packaging, converting sand to metallurgical grade silicon. And I think you have your deadline for the assignments coming up on Wednesday next week. So we'll be having a session on Tuesday. In that session, in case you have, I cannot like reveal the answers to the assignment questions to be submitted, but in case you have any doubts, I can give you hints so that you can like prepare your answers accordingly for the assignment submission. So that is one another activity we will be starting from the next week onwards. Last like 10 to 15 minutes or 20 minutes, we'll like exclusively click for this doubt clearing sessions. And in case you can like mail to me the doubt in like beforehand, I can prepare a slide or so and so. Otherwise, I'll have to just explain with whatever I have. So, but I suggest that you go through the assignments beforehand, and if you feel that you're not able to get any answers, either write to me or we can discuss during the last 10 to 15 minutes in the session on next Tuesday. So again, coming back to a question, the first step in IC manufacturing is dust. I think this is a rather straightforward process. Now, before you start manufacturing any IC, what do you do? Like wafer fabrication and sorting, single crystal growth, packaging, converting sand to MGS. People are joining now, I think.
B.
Sorry, D or D.
Is it B? B.
D. No. People have written, like many people are replying in the chat box. One thing is that if you're using the chat box, I won't be able to see. So please unmute and speak. A few people have written down D in the chat window. So the answer is D. Converting SATs to MGS. So all the people like who have messaged in the site window, please do unmute and speak. So first step is material preparation. That is sand we have to convert to MGS. Then we have to convert the polycrystalline MGS into the single crystal EGS. and then the single crystal EGS has to be converted into a single ingot using the Czochralski and flat zone. And after that, we have processes like wafer fabrication and sorting, packaging, and finally electrical testing. So these are the 5 steps in IC manufacturing. So is that clear for all of you? The first step is material preparation or converting sand to metallurgical grade silicon which has impurities in the range of parts per million. Then we'll convert the MGS into EGS with impurities in parts per billion. Then we'll convert it into the single crystal ingot using Czochralski and float zone. And once we have the wafer, there starts the process where we slice it, we fabricate and salt it. And then we'll have to apply a particular photo mask on top and we'll have to design the electrical circuit. And finally, this electrical circuit has to be tested. So these are the 5 steps that are associated with IC manufacturing. So next is the portion of a wafer that is a standalone unit is called dash.
Die.
Yeah. So this is our wafer. Our wafer has a primary flat and we have edge chips, and then in between we have regions that are used for the electrical testing part. Those are known as test dies, and the functional standalone unit is known as a chip. So these units are separated from each other using scribe lights. So these are the things that you can find on a silicon wafer. So I hope it's clear for all of you. These all were discussed in the lectures, I think. So portion of a wafer that is a standalone unit is called a die. Only on these chips we will be able to create the requisite circuits. The test dies will be used for the electrical testing. Edge chips as such are not used, and these are separated from each other using scribe lights. So this is the primary flat. Since it has only primary flat, can anybody tell me what type of a wafer it is? Whether it's P100 or N100?
P111.
Yeah. Okay. So I think again I have people waiting for me. No, somebody left. It seems. Device miniaturization is dependent on which of the following steps: layering, doping, patterning, and heat treatment. So in the first set of lectures, you might have seen that as each year passes, the size of the circuits goes on becoming smaller and smaller, and which is the factor that causes it to become smaller and smaller. That is device miniaturization. So it is so is it layering, doping, patterning, or heat treatment?
Patterning.
Hmm. Anybody else? Sorry, what was your answer?
Patterning.
Okay, so why can you explain?
I think that is the process through which you use a reticle to make patterns on the photomask
Okay,
and
and
then transfer it to the wafer.
yeah, so patterning is the process where you transfer the circuit. So as you can make smaller and smaller patterns, the amount of circuits that can add per area of the wafer becomes more and more, right? So it leads to device miniaturization. That is, per small area of the wafer, the amount of electrical circuits that we can pattern becomes more and more. So that is why somebody has unmuted and it's causing some interference, I think. So device miniaturization is dependent upon the patterning process. So as you can make smaller and smaller patterns, you can apply to create much closely spaced circuits on your wafer, and that in turn will help us in device miniaturization. So is that clear? So next question is, lateral spread is minimum for dash doping technique.
ALD? LD process?
Anybody else? The answer is ion implantation. So can you tell me what are the different doping techniques, anybody? Like what are the different doping techniques? Like, a few main topics were discussed. So in that, what are the different doping techniques?
Is it thermal diffusion and ion implantation?
Yeah. So one is thermal diffusion and one is ion implantation. So what happens is that in case what is meant by lateral spread, suppose you want to embed your ion. So doping means that you're adding an additional element that causes either an extra electron or a vacancy in a particular semiconductor. So in thermal diffusion, what happens is that once the ions are deposited on the surface, they are driven by virtue of heat. So we cannot control the lateral extent or the sidewise extent to which these ions will penetrate. But in case of ion implantation, the high energy ion will be bombarded onto the surface of the substrate or the semiconductor. So what happens is that it will penetrate much in depth without having sideways dispersion or sideways spread. So that is why lateral spread is minimum for ion implantation technique. So is that clear? So in diffusion, it is done at a high temperature, and diffusion takes place by virtue of this temperature. But in case of ion implantation, the dopant atoms will be ionized and it will be accelerated towards the substrate and then impinged and embedded. So the ions will penetrate farther without going sideways. But in thermal diffusion, once on the surface, they can diffuse in whatever directions they like. So the lateral spread will be more in case of thermal diffusion. Is that clear?
Yes.
Yeah. So next is, deep trenches with high aspect ratios are effectively coated by dash. So deep trenches means that high aspect ratio means that the circuit or the pattern on top of the wafer that we are creating using the oxide layer will have a much more depth compared to its breadth, or its aspect ratio will be very high. That is, one dimension will be much different when compared to the another dimension. So such materials can be effective coated, such features can be effectively coated by using dash technique. Anybody? Like not the answer. Can anybody tell me what are the different coating techniques that you do? Like in case of semiconductor materials?
Spin coating.
Okay. Film coating is a type of chemical deposition or physical deposition.
Chemical.
No, there are no chemical reaction taking place, right? You're physically, like suppose in case of spin coating, what do? You like dispense a drop of the coating material on top of the substrate. You fit the substrate into the equipment, and by motion of the centrifugal force, what happens is the material will spread onto the surface of the substrate. So that is what is spin coating. But
Yeah. So it's not chemical.
no reactions are there as such. But in certain coating techniques, have you heard of physical vapor deposition and chemical vapor deposition?
Yes.
Yeah. So such deep trench-like features are done. You are coated using the chemical vapor deposition or the CVD process. So what happens is that you will have your material that you want to coat. It will be heated. It will be vaporized, and once vaporized, it will go and it will react onto the surface of the substrate that you want. In physical vapor deposition, again your material will be vaporized, but instead of being like chemically reacting with the substrate, it will be deposited as such onto the material. Like the substrate will be inside the same chamber where the vaporization take place, and they just go and just embed on the surface. There is no reaction taking place. But in chemical vapor deposition, it is such that however complex your features are, these molecules will penetrate and they'll chemically react because they have an affinity towards the substrate. So deep trenches with high aspect ratios are effectively coated using chemical vapor deposition technique. So next question is, current levels of device integration is called dash. The current ones we are using. Anybody?
ULSI.
Yeah. So can you tell me what is ULSI? Like greater than how? Like there will be a how? Like number of chips per piece or number of
Number
components?
of component
Yeah.
number of component per chip is 10 to power 7 or 10 to power 8.
Yeah. So this is the current ones we are having is ULSI, that is ultra large scale integration. It will be such that the number of components per chip will be greater than 10 power 6. That is usually in the range of 10 power 7 or 10 power 8. So that is ULSI. So now a random question I want to ask. Can anybody tell me what is Moore's law?
The number of ICs double every 2 years.
Yeah, and in your assignment, I think the first question is regarding Moore's law, right? So that is one thing. So next question is, which of the following is an example of a process to produce grown layers? That is, we know that on our substrate, we need to grow multiple layers of oxides, which are then etched during the patterning process so as to create our circuits. So which of the following is a process to produce such grown layers? MBE is
Sputtering.
okay. One more try. Anybody else with any other opinion?
Oxidation.
Oxidation.
Yeah. So the answer is oxidation. So actually there are two ways in which we can do layering process on a substrate. One is to produce a grown layer and one is to produce a deposited layer. So first grown layer, what we do is that we either oxidize the one material on top or we do nitridation such that the new layer grows on the surface of the substrate. On the other hand, in a deposited layer, we can externally deposit by driving ions using the chemical vapor deposition process or using physical evaporation, sputtering, or electroplating. Like it can produce layers, but you should note the word grown layer or deposited layer. The answer sputtering would have been corrected if it was a deposited layer. For a grown layer, we can use either oxidation or nitridation. So is that clear?
Yes.
Yeah. So next question is, so before going to next question, can anybody tell me what is the difference between float zone technique and Czochralski? Like once we have an electronic gate silicon, it has to be converted into the single crystal ingot, right? So we have two processes, that is Czochralski and float zone. So one person please tell me what is float zone technique and the other person, anybody can tell me what is Czochralski. So that it's easier to answer this question in case people are not familiar with Czochralski or float zone. Anybody? If you have prepared notes, you can go through your notes and just tell me either is fine what is float zone technique and what is Czochralski. So I think anybody? Yeah.
In Czochralski, you introduce a seed crystal into a furnace
Yeah.
and then you heat it with the help of RF heating coils.
Okay.
and then you probably pull it out with the formation of the
Single crystal. Yeah.
ingot.
Yeah. So one person has told me what is Chokralski. Now another person, what is float zone technique for producing single crystals? Anybody? Yeah, somebody has unmuted. What is the float zone process? Like, yeah, the doubt that one has posted in the messaging section, I should address it towards the end. So first we'll finish this. What is float zone process? Like one person told me what is Chokralski. Next is float zone. Anybody? Even a very vague explanation is fine.
Polycrystalline EGC is melted and it is placed on a seed crystal.
Okay, like so basically in float zone what happens is that we'll do localized heating of the ingot. The heated portion will be in contact with seed, and while heating, the whatever part that is in contact with the seed crystal, what happens? It forms a localized molten zone, and finally it cools. And during the cooling process, what happens is that since it is in contact with the seed that we require, this differential cooling process will gradually lead to the formation of our final single crystal area. So I think with this picture I can. So in Chokralski, as you've already mentioned, we'll create a molten pool of the MGS, and what happens is that the seed crystal will be in contact, and in a rotation motion the portion along with the seed will be taken out and gradually it cools down, and finally we'll get the single crystal effect. In EGS what happens is that here if we can see a localized heating is created, and heating is done in contact with the seed crystal. So as we gradually go on heating from one end to the another, this rod will be converted from the polycrystalline seed to the single crystal EGS. So that is what happens in Chokralski and float zone process. So knowing that, now let us come back to our question. So why is the float zone technique harder to implement for larger wafers? Like we know what float zone is, right? So why is it difficult for larger wafers? Anybody?
This is harder to get.
Okay. So basically, the float zone technique is such that localized heating and cooling takes place, right? For larger wafers, uniform melting will become an issue because the larger the material, so we can do only tiny pieces of ingots at a time. So suppose we have a large wafer and there won't be like uniform heating and cooling, and this difference in the rate of solidification process can produce stresses and defects. So that is the reason why float zone technique is harder to implement for larger wafers. So if it's a very small ingot and a very small wafer that we required, it will be equal. So we know that it will be equally heated in all regions and equally cools down. But for larger wafers, there is a difference in this cooling and heating rate, right? And so this will produce stresses and defects, which are not at all advisable when we are creating electronic grade materials. So is that clear? So next is somebody has to tell me the equations for converting silica into MgS and then MgS into EgS. So we have a set of reactions, right? So these are the kind of descriptive questions that might come up during your examination. The equation, so either you'll have to write down the equations or an equation will be given to you and you'll have to identify which step that is corresponds to. So what are the equations for converting silica into MgS and MgS to EgS? Anybody? Like how do you convert? Yeah, tell. Okay, then this is, yeah, to get silica, SiO and carbon monoxide, right? Yeah, so that is the first step, converting silica into metallurgical grade silicon. Now we have the metallurgical grade silicon, and before we discuss the Siemens process, right? So what is the equations corresponding to Siemens process? Somebody had messaged, I think. Can you just unmute and speak, whoever that is? So I'm not understanding. Like, so Shrita, please show the slides from the beginning, in the sense the questions in the beginning, or like, what do you mean by slides from the beginning? In the meantime, can other people start figuring out what is the equations for Siemens process? First set of answers is correct. First, you have to react SiO2 with carbon to get silicon carbide, then silicon carbide plus SiO2 to get silica, silicon monoxide, and carbon monoxide. And next is the Siemens process. And finally, you will end up with electronic grade silicon. So, one person had answered actually what was the Siemens process, or on the same lines. First, anybody can answer? MGS to EGS conversion. So first silicon will be reacted with HCl to give. In Siemens process, the first step is that silicon is reacted with HCl. So can anybody tell me what will be the product after that? Si plus HCl. Yeah. Then now the trichlorosilane will be reacted with, yeah, reduced with hydrogen to give Si and 6HCl. So first is silica into MgS. We already know silicon carbide plus SiO2, Si, SiO and carbon monoxide. And then in Siemens process, it's carried out on a fluidized well reactor. Silicon plus HCl gives SiHCl3 plus hydrogen. Then again, it's reduced in presence of hydrogen to give Si and 6HCl. So these are the processes by which silica is converted into MgS, and then MgS is converted into EGS. So you have two additional questions that you can, like this PPT will be uploaded in the page for the live tutorial session, and there you can see the question. So first question is, starting from a blank N-type silicon wafer, show all the steps that are required to create a single PN junction where electrical contacts for both P and N should be at the top. So you have a similar problem that is discussed in week 1 lecture. So on same lines, if you start thinking, you'll be able to find the answer to this question. So next is 15th question. Predict the breakdown of the Moore's law. When will the Moore's law get saturated? And you'll have to justify why. So these two questions I'll be asking the answers in the next week. So please try to answer while you come. So yeah, yeah. Yeah, because it's a repeated looped process. It's not a reaction that ends here. It will be continued until the impurities are reduced. That is the reason. Yeah. So these two last two questions, please try to answer. So these are the questions for today. So please, either you can post your additional questions in the discussion forum or the mail ID that I showed previously, santhra.pmrf@gmail.com. So now I'll come back to a few questions that people had posted. Ma'am, all the questions which was discussed previously, I think you might have joined a little late today. So all these questions along with the slide and whatever material I have will be uploaded in the like live tutorial section of the NPTEL portal. So don't worry, you will have like direct access to this PPT if that is the case. Is that fine for you? Yeah, my like I'll dictate it. Sant SANTHRA dot PMRF IITM at gmail.com. Yeah. So one person had posted in between. Please explain the this aspect ratio PVD like sputtering. So, K5, can you just unmute and let me know what was the actual doubt? And like, what is PVD like sputtering, and what do you mean by, I don't know, like I'm not able to understand what his doubt is. PL, explain this aspect ratio PVD like sputtering. Is he in the chat? Question number 9. Okay. Deep trenches with high aspect ratios are effectively coated by a dash, and the answer was CVD. So first, you want me to explain what is deep trench? Is that it? And why? So while we are doing a part of us, so first we have the substrate. On that we'll grow a layer of oxide, and this oxide will be etched to create different features using photoresist. We are in the foregoing steps, right? So when we are creating such features, sometimes the feature may be in such a shape that one dimension is very, very small or large compared to the another dimension. That is the high aspect ratio deep trenches that you come across in these electronic materials. So suppose you want to deposit the next layer of materials on such features, which process would you use? Would you go for CVD or would you go for PVD and so on? So that is the high aspect ratio deep trenches when it comes to electronical grade silicon. So is that first part clear? Yes. That is what, well, suppose one dimension is much large, you can imagine where there is a sequence of crests and valleys, right? So yeah, in turn you can interpret them as being roughness. That is also true. Yeah. So now PVD and CVD, and why CVD? PVD we know that stands for physical vapor deposition. CVD on the other hand stands for chemical vapor deposition. In PVD what we do is that atoms are moved towards the substrate and they're physically deposited onto the substrate. But in CVD what happens is that these gaseous molecules or atoms will react with the substrate. So that is why PVD is suitable for coatings in applications that in which the aspect ratio is much lesser compared to that involved with these high roughness deep trenches and so and so. But when we are using chemical deposition, what happens is that these gaseous atoms will have an affinity for the material of the substrate. As a result, they'll have a greater tendency to coat evenly on the substrate. That is why we prefer chemical vapor deposition for such deep trenches having rough features. Okay. Anybody else with any general or topic related doubts? Okay, tell me. Yeah. Okay. Yeah, like yeah, you have the silicon wafer, so it will basically be a round shaped material, right? So if it is as such round, we won't be able to identify whether the wafer that we are having in hand is a P type or N type. So in order to differentiate between the different types of wafer available to us, a certain portion will be given a cut. Like some will be having no cuts, only just one side will be flat. Some will be such that both sides are flat. One will be such that one side is flat and there is a cut at 45. And one will be such that one is a flat one and one will be at 90 degrees. So using these cuttings, we will be able to understand which P type or N type wafer we have in our hand. Yeah. Like these are very thin materials. So a part of that will be cut such that suppose you imagine that you have a round paper and you just cut one edge so that one edge instead of being round it is flat. So that is the primary flat. So with respect to this primary flat, if you're cutting at 45 or cutting at 90 or cutting on exactly the opposite side, we can identify or distinguish between these wafers. And each year as we pass, the wafers are becoming thinner and thinner, right? Yeah, so next, Sisir had unmuted, please ask. Sorry, what part? Homoepitaxial growth. In which section? Like homoepitaxial growth, yeah, like basically we are depositing the same material as that of the substrate, right? So that, yeah. So basically, yeah, it can be that either we want to deposit same material having different plane orientation, or if we want to adjust the thickness. Yeah. And one more thing where we can use this homoepitaxial case is that even if we have the same material, you can change the level of doping on each layer. Suppose if it's the same material and in one layer you have so and so concentration of doping and in the next one layer you want a different concentration of doping, that is also one place where you can use homoepitaxial case. Because if you are doing a continuous process, it might be able to very difficult to control the level to which, because there will be issues like lateral spread and so and so. Suppose in one layer you control and in the next layer you do a different concentration. Using homoepitaxy, it will be a much more controlled process. Because when it comes to electronic materials, like each of these things will make a large difference, right? Yeah. Anything else? Yeah, I think that is all. People don't have any questions this week. So today we have a rather short session. From next week onwards, we'll go for 2 hour sessions each. Today we are cutting short because one is because it's an introduction and I don't want to bore you. Another is that I'm having some health issues and that's why. So next week onwards we'll be having 2 hour sessions, and I request all of you to join correctly at 6 p.m. And this year NPTEL has also introduced an attendance system. Before, they didn't count the number of students that attended each session. So at this time, they have asked us to give the attendance sheet as well. So they'll be able to see like what time you're joining and leaving, or if you're just fluctuating between joining and leaving and so and so. So, and whatever queries you have, please do post it either on the discussion forum or you can mail it to me. And please go through your assignment questions. And in case you have any doubts, please do talk to me on the coming session. So I hope such a session is useful for all of you. Thank you so much for joining. Thank you and bye bye. Yeah, yeah. Thank you so much. Yeah. I'll be sharing it. Like immediately, I'll share it to the NPTEL team. They will eventually update it in the portal. So that is the system. Yeah.